Hello friends, welcome back to Synapsera. Have you ever wondered how neural networks actually learn? Or how your phone somehow recognizes your face the moment you unlock it? And how Netflix always seems to know exactly what show you'll binge next? Behind all of these incredible technologies lies one simple, elegant idea. It's called gradient descent, the fundamental algorithm that powers modern machine learning. Today, we're going to break it down and understand exactly how it works step by step. We'll visualize it beautifully, watching our model descend toward the minimum, and we'll make sense of the math without getting lost in equations. So by the end of this, you'll not only know what gradient descent does, you will see it in action. Let's dive in. At its core, gradient descent solves a fundamental question. How do we find the minimum of a function? In calculus class, we learned one method. First, take the derivative. Second, set it equal to 0 and solve. Third, verify it's a minimum by checking the second derivative. For example, to minimize f of x equals x squared minus 4x plus 3, we find f prime of x equals 2x minus 4 equals 0, giving us x equals 2. This works great for simple functions. But what if our function has 1,000 variables? What if there's no closed form solution to f prime equals 0? What if we only have numerical outputs from the function, not a formula? What if computing the derivative symbolically is incredibly complex? In these real-world scenarios, the calculus approach becomes impractical or even impossible. This is where we need a numerical method, an algorithm that works with numbers, not symbols. Enter gradient descent. Before we look at the equations, let's build an intuition for how this algorithm works. Imagine you're standing on a foggy hillside. Your goal is to reach the bottom, but you can't see more than a few feet in any direction. What do? Here you are, somewhere on the hill. Down there is your goal, the lowest point. But the fog prevents you from seeing the entire landscape. You can't just look and walk straight to the bottom. However, you can feel which way the ground slopes. At your current position, you can determine which direction is downhill. In mathematical terms, you can compute the slope, the gradient, at your location. This is your key piece of information. So here's the strategy. Take a small step in the downhill direction. Then, at your new position, check the slope again. Take another small step downhill, and another, and another. Each step moves you closer to the bottom. By following this simple rule, always step in the direction of steepest descent, you trace out a path down the hill. Eventually, you reach a point where every direction leads upward. You've found a valley, a local minimum. Success. This is the key insight behind gradient descent. Use the slope or gradient to determine which direction takes you downhill. It's that simple and that powerful. Okay, so we keep mentioning this gradient. What exactly is it? Let's make this crystal clear. For functions of a single variable, the gradient is simply the derivative. If f of x equals x squared, then the gradient is df dx, which equals 2x. In one dimension, the words gradient and derivative mean the same thing. Let's see what this means visually. Here's our parabola. F of x equals x squared. At x equals negative 2, the gradient is negative 4. Notice the tangent line slopes downward to the right. That's a negative slope. At x equals 0, the gradient is 0. The tangent line is perfectly horizontal. This is our minimum. At x equals 2, the gradient is positive 4. The slope goes upward to the right. Here's what you need to remember. When the gradient is positive, the function is increasing. When it's negative, the function is decreasing. And when it's 0, you found a potential minimum or maximum. For functions of multiple variables, like f of xy equals x squared plus y squared, the gradient becomes a vector. It has one component for each variable, the partial derivative with respect to that variable. This vector points in the direction of steepest ascent. But the core idea remains the same. The gradient tells us about the slope. Now we're ready for the heart of the algorithm. This single equation is what makes gradient descent work. Let's break it down piece by piece. Here it is. Xn plus 1 equals xn minus alpha times the gradient of f at xn. This might look intimidating, but stick with me, it's actually quite simple. Xn is our current position. It's where we are right now in our search for the minimum. Xn plus 1 is our next position. It's where we are moving to. This formula tells us how to calculate our next step. Alpha is called the learning rate or step size. It's a positive number that controls how large our steps are. Think of it as how confidently we stride down the hill. Too large and we might overshoot. Too small and we'll take forever. Choosing alpha wisely is crucial. The gradient, nabla f of x minus n, is the slope at our current position. It tells us the direction of steepest ascent, which way is uphill from where we stand. And here's the critical part, the minus sign. We don't move in the direction of the gradient. We move in the opposite direction. Why? Because the gradient points uphill, but we want to go downhill. This negative sign is what makes it gradient descent, not gradient ascent. Let's put this in plain English. Start at position xn. Calculate which way is uphill. That's the gradient. Take a small step, size alpha, in the opposite direction, downhill. Arrive at your new position, xn plus 1. That's it. That's gradient descent. Theory is great, but let's apply this to a concrete example. We'll use a function that's interesting but still manageable. Here's our function. F of x equals x squared times cosine of x minus x, all divided by 10. Why this function? It has multiple local minima, so it's non-trivial. It's complicated enough that solving it analytically would be tedious, and it's perfect for visualizing how gradient descent works. To use gradient descent, we need the gradient. Let's compute it step by step. The gradient of f is 1/10 times the derivative of x squared cosine x minus x. Using the product rule and chain rule from calculus, this becomes 1/10 times 2x cosine x minus x squared sine x minus 1. So our gradient formula is nabla f of x equals 2x cosine x minus x squared sine x minus 1, all divided by 10. This might look messy, but that's fine. The computer can evaluate this numerically at any x value we need. We don't need to simplify it further. This is the formula our algorithm will use. Let's now visualize the function we'll be working with. Our function is fx equals x squared cos x, x divided by 10. It's a slightly wavy, nonlinear curve, simple enough to see what's happening, but rich enough to show all the key ideas of gradient descent. As we plot this function, notice how it dips and rises. These oscillations create multiple valleys or regions where the function reaches local minima. Each red point marks one of those local minima points where the function stops decreasing and begins to rise again. These are exactly the kind of points gradient descent tries to find automatically. To understand how, let's look at the gradient, the slope, at different positions along the curve. Here at x equals 2, the slope is negative. That means the curve is slanting downward to the right. In gradient descent, this would tell us to move rightward toward a smaller value of fx. At x equals 5, the slope is positive, the curve rises to the right. So the algorithm would move leftward, again heading toward a lower point. And around x equals 3.72, the slope is almost 0. That's a flat region, a valley bottom, meaning we've likely reached a local minimum. So here's what we've learned. The gradient tells us the slope at every point. A negative gradient means the function is decreasing. A positive gradient means it's increasing. And when the gradient reaches 0, we're at a potential minimum. Now for the exciting part, let's watch gradient descent in action, step by step. We'll start at x equals 6 with a learning rate of 0.2. Remember our formula. X next equals x current minus alpha times the gradient. Step 1. First, we calculate the gradient at our current position. The gradient at 6 is about 2.058. See this red tangent line? That's showing us the slope. Now we update. x1 equals 6 minus 0.2 times 2.058, which gives us 5.59. Watch as we move in the negative gradient direction, downhill. Step 2. At our new position, the gradient is 2.758. So x2 equals 5.59 minus 0.2 times 2.758, giving us 5.04. We're sliding down the hill, getting closer to the valley. Step 3. The gradient is now 2.626. Another update brings us to x3 equals 4.51. Continuing this process. Step 4, Step 5, Step 6. Look at this beautiful path we're tracing. Each step takes us closer to the minimum, and we've converged. After 10 steps, we're at x equals approximately 3.728, where the function value is about negative 1.53. We found a local minimum. Let's wrap up with a mathematical summary of what we've learned. The gradient descent algorithm follows 4 simple steps. 1. Start with an initial guess, x0. 2. Compute the gradient at that point. 3. Update your position using this formula. X next equals x current minus alpha times the gradient. 4. Repeat until convergence. Here are the key mathematical insights to remember. First, the gradient points toward the steepest ascent, uphill. Second, the negative gradient points toward the steepest descent, downhill. That's why we subtract it. Third, the learning rate alpha controls our step size. Too large and we might overshoot. Too small and convergence takes forever. Fourth, we stop when the gradient is approximately 0. That means we're at a minimum. Why does this work? At each step, we move in the direction that decreases the function value the most. By taking small steps, we ensure we don't overshoot and miss the minimum. Here's the mathematical guarantee. If the function is smooth and alpha is small enough, each step will decrease fx. We have f at x next is less than f at x current. And there you have it. This simple mathematical idea, following the negative gradient downhill, powers modern AI and machine learning. From training neural networks to optimizing complex systems, gradient descent is everywhere. Let us see a simulation to understand the process in a better manner. First, let's meet our function. This is a wavy bowl. Imagine a landscape with hills and valleys. Mathematically, it's fxy equals x squared plus y squared plus sine 5x plus sine 5y. Notice the multiple valleys here. The deepest point right here at the center is our global minimum. That's where we want to end up. But here's the challenge. What if we start somewhere random on this landscape? How do we find our way down? We're going to try 4 different starting points. See these colored squares? Each one represents a different initial guess. Watch what happens when we apply gradient descent from each location. Here's the same landscape from above, shown as a contour map. The darker regions are valleys, lighter regions are peaks. Look at these 4 paths: red, cyan, yellow, and teal. Each one starts from a different location, but they all snake their way down to that yellow star in the center. Notice how the paths aren't straight lines. They follow the steepest descent at each point, which creates these curved trajectories. It's like water flowing downhill. It doesn't go straight down. It follows the natural contours of the land. And here's the beautiful part. Despite starting from completely different locations, all 4 paths converge to the same minimum. This is gradient descent working exactly as designed. Now let's analyze where gradient descent actually explores. This heat map shows the density of visited points. See these bright red areas? These are places the algorithm spent the most time. Notice how they cluster around the paths we just saw, with the brightest spot right at the minimum. These side panels show us something interesting. The x distribution shows that most exploration happens near x equals 0, which makes sense. That's where our minimum is. Same story with the y distribution. The algorithm naturally concentrates its search where it matters most. And this bottom panel, it shows step sizes. Notice how most steps are small. That's the algorithm, being careful as it descends, taking smaller steps as it gets closer to the bottom. It's like being cautious when walking down a steep hill. Let's dig into the numbers. This dashboard shows us 4 key metrics. Top left, the function value over time. Watch how each colored line drops rapidly at first, then flattens out. That sharp drop, that's gradient descent, doing its job, quickly reducing the function value. Top right, how far we are from the minimum. Again, rapid decrease, then stabilization. Some paths take longer routes, but they all get there. Bottom left is crucial. This shows the gradient magnitude on a log scale. Remember, the gradient tells us how steep the landscape is. As we approach the minimum, the gradient approaches 0, that's when the algorithm knows to stop. And bottom right gives us the bird's eye view again, with arrows showing the initial direction. See how each path is efficient? No wasted movement, just smart, directed descent. Now let's watch this unfold in real time. On the left, we see the paths building step by step. On the right, the objective values dropping with each iteration. Watch carefully, see how the points move more slowly as they approach the center? That's because the gradient is getting smaller. The algorithm is naturally slowing down as it nears the goal. Here's the same process in 3D. As the view rotates, you can really see how the paths descend through the landscape. Notice how they avoid the peaks and flow through the valleys. This perspective makes it clear gradient descent doesn't just randomly search. It follows the geometry of the function, always moving in the direction of steepest descent. This animation shows exploration density building up over time. The heat map starts cold and gradually heats up where the algorithm visits most. Watch how the hotspots form along the paths. This gives us insight into the algorithm's behavior, where it explores, where it lingers, and where it quickly passes through. Finally, let's see everything at once. 4 panels, 4 paths, all updating simultaneously. This is the complete picture of gradient descent in action. Objective values falling, distances shrinking, gradients decreasing, and paths converging, all telling the same story of successful optimization. If you want to create these visualizations yourself, I've linked the full Python code in the description. Try different functions, different starting points, different learning rates, see what patterns emerge. Thanks for watching. If this helped gradient descent finally click for you, hit that like button and subscribe for more mathematical visualizations. See you in the next one.